Hi everyone, my name is Thibaut Neveu, and so I'm going to talk today about one of the projects I am working on since last 3 months. And so first we are going to dive into this project a little bit, and then I will just show you a little demonstration. And at the end we are going to see how does one of the algorithms that I use to solve the environment is working. So here this is like the reinforcement learning framework, the basic one. So you always have an agent which is trying to step into the environment by taking actions. So it can be good action or random action to explore the environment. And then the environment just give back a state and a reward. So if you're using Python or with TensorFlow, you might know or heard about GYM. So this is a reinforcement learning library made by OpenAI. So this is a very good library if you want to dive into reinforcement learning because you have a lot of different problems to solve. You can go from Atari games, from solving robotics problems, like trying to grasp an object and just play with the objects, learn to drive, and many stuff like that, learn a humanoid how to walk into a room. So you can literally make a lot of good stuff with GYM. This is a good thing. But now we have something which is new. We have TensorFlow.js into the browser using JavaScript. So the question is, do we have something here? Do we have an environment to play around with reinforcement learning but into the browser? I was very stuck with that because I wanted to just use TensorFlow.js with reinforcement learning algorithm, but I was like, okay, there is no environment for that. So this is why I think about Metacar. So Metacar is a reinforcement learning environment for self-driving cars into the browser. So basically you can just code your agents, so in vanilla JavaScript, or use TensorFlow.js to create a deep learning models for your reinforcement learning agents, and take action into the environment with the goal to teach to the agent how to drive and how to behave into the city to just drive with other vehicles. And then the environment just gives you a state and a reward. So there is three main components in the environment right now. So there is the agent, which is the red cars. There is, of course, the road and the other vehicles. So in the real world, self-driving vehicles are using sensors to map the environment and to try to create a representation of the world surrounding. And one of the most famous sensors which is used is the LiDAR. And so in this environment, here, this square that you can see here, it's kind of a LiDAR which just try to represent the environment. So this is the state of the agent. This is what the agent can see. And each one here is a value that can take a particular values depending on what it sees in the environment. So it can be a particular value if the agent sees a road, a particular value for vehicles, or just if the agent sees a road, it will take a particular value. So at the end, the state of the agent, what the agent can see, is just a vector of different values like this. Then you can choose which type of action you want to take into the environment. You can choose discrete action, for instance. So here, discrete action is very good for beginners if you just want to start with reinforcement learning, but you don't have a lot of knowledge. Usually, you might want to take discrete action, like just going up, down, left, or right. Going up, you just take the vehicle, just take a given amount of speed, go forward. Going down, going backward. On left, the vehicle just go 90 degrees to the left or 90 degrees to the right. So this is very simple on a very simple model, which is far away from the real vehicles, far away from the reality. But this is good to start to dive into reinforcement learning. Or if you want to go in more advanced stuff with reinforcement learning, you can use the continuous values. So this is continuous action, so you have two values. One value for the acceleration, going from -1 to 1, and one action for the steering angle of the car to turn left or right, going from -1 to 1, 2. But this is much more difficult for this part, but you can just choose. And this is why I made Metacar to be for everyone, just for beginners and also for advanced developers. Do you have any questions before we move to the reward? Okay, so I have a question for you here. So let's consider that the reward for this environment is -1 if the red cars crash another vehicle or quit the road, and 0 otherwise. Do you see any problem with this reward? Because we want the car to learn how to drive into the environment. If we set this reward, do you see something which is wrong here? Yeah?
It won't do anything.
Yeah. Sure, the car will just don't do anything. So this is very problematic, but when I just started with the reinforcement learning, I set this reward out, it was absolutely not working, and I was like, okay, I make something wrong here. But I mean, here this is a very simple example, but usually when you work with with difficult environment, you have a lot of problem with that when you have a reward, but you expect your agent to do something, but the agent understands the reward in a different way. So now let's consider this reward. So this is maybe a little bit tricky. So here -1 if the car crashes another vehicle or quits the road, and 1 if the speed is different from 0, and 0 otherwise. Do you think it is a good thing or not?
Yes.
It is almost a good thing.
Almost, yeah.
Yeah. The problem is with this reward is that, let's say I am a car, and I have an acceleration, so I will take some time before to reach my maximum speed. But let's say I want the speed to be different from 0. The car just has to do that to get the maximum amount of reward. So basically, the agent will be going to be stuck into a local minima where the agent will just have the maximum amount of reward possible, and she will be happy with that. So she will be happy to do something like, okay, my speed is different from 0, so it's okay. So this reward is still not good enough. So the reward that I am using in my environment is this one. This is just a little bit different. So this is -1 for crash and quit the road. And then I use max of 0 and the speed of the car divided by the maximum possible speed. So then I have a reward which go from 0 to 1. So it takes a long time for the cars to reach the maximum reward possible. So then the car have to learn how to turn and how to pass over other vehicles, and basically how to behave into the environment to be able to reach the maximum possible reward. So this is the reward I use. So this is not a perfect reward, there is some downside, but this is enough to solve the environment that I will show you after. Yeah?
Why would you not consider anything like position of where you are?
I tried that. I mean, I tried to say, okay, I want you to move into the space from different position, but it was the car was like sometimes doing some stuff like just going here, and when they see another car, they just turn like this. And the car was happy because she make a step into the environment, like changing the position. So it's still not good enough. Yeah.
Have you tried some exponential
I didn't try that, no. But yeah, but what is good is that with Metacar you can customize everything. So you can also customize your reward function if you want to just make it fit your need. Okay, so I'm going to show you a little demonstration of that. So here is the GitHub. If you want to check out, there is also a documentation where all you need to install the project and start to create your environment and to customize everything. So you can basically create your own environment and customize everything, like the reward or the speed of the cars, the speed of other vehicles in the map to make it more difficult. So you can change all of that stuff. So here is a little city, so without agent here, but this is just to show you how does the city looks like without the agent. So here just basically all it takes to create an environment. And so we are going to look at 4 demonstrations with different level of different complexity. So the first one is just a level with discrete action with no other vehicles. So here I am just controlling the car by myself here. But as you can see here on the bottom, I can see the LiDAR, the state of the LiDAR. So if I move the car, the state change like this.
It's like a radar.
Yeah. And so here the algorithm is just using a Q-learning table. So there is no TensorFlow.js which is used here. I just use vanilla JavaScript to solve the environment with a Q table. So this is like the hello world of reinforcement learning if you want to dive into that. And if I load the train agent, so this is an agent which is already trained. What I have here is a preview of my Q table. So for each state of the LiDAR, I have the different action that the car can take, and with different value. On the value say how good it is to take this action for a particular state. Basically the Q table is just little like this because it's a very simple environment. And I also customize the size of the LiDAR with the number of points to make it very easy to solve. And if I say make it play, the car just drive like this. So yeah, so that was the most easy one to solve. Then there is this one, still with discrete action. And as you can see, the car just turn like this. And if I just stop to press the up button, the car just stopped also. So this is very easy. So here this is an algorithm which uses TensorFlow.js. So this is a policy gradient algorithm. And if I load the agent, just the car just. So here it takes about 30 minutes for the agent to be trained like this. So it is quite yeah, it's not so long to reach this level. And then we have continuous actions. So here, if you can see, like there is an acceleration, so the car don't reach the maximum speed directly at the beginning. There is some time before to reach the maximum speed, and the control is much more realistic. If I just stop to accelerate, the car just continue on the road, and I can also go on the other backward like this. And same so here it takes about 1 hour to reach this behavior. Yeah, so this is still not perfect, but enough to say that it is solved. Yeah. So for the moment it's good because there is no other vehicles. So okay, so let's use the same algorithm but with other vehicles. So the same one but with other vehicles. So you can see this agent is very dangerous. So it crashed. Okay. So here this is how does it look for an agent to be trained into the environment. So this is just I just make it like this to show you how it looks when the agent is just training. Just try to explore the environment and to see which action go to just fail and which action is good or which action is bad. I also include some graphic here to see, and we can see here the LiDAR. So this is basically very interesting. Here you can see very in much more realistic way what the car can see. With other vehicles in white, the floor in green, and the road in like this. Okay, let's try again. Yes.
Just use the left-hand side of the road.
Okay, so we can also try to. Okay, I control the car here. I will try on the other side. Okay. Okay. She's not very confident at all.
Should get this algorithm in Tesla's cars.
Yeah, that's okay. So yeah, I mean, so the goal at the end is to make this car being able to drive like other vehicles and without being dangerous. So there is a lot of things to do to reach this point. But yeah, and also my goal will be to add other things like pedestrians or bikes to make it more realistic, like a true city, and to try to make vehicles to drive along and to be safe. Yeah. Do you have any question?
So,
Yeah.
so in that next step where you want to keep the car on one side of the road,
Yeah.
how do you go about implementing that it doesn't cross?
You mean on this side, on
Yeah.
this side? I didn't implement anything on that. I mean, I think that, you know, with the LiDAR, you can see each, when you, okay, I'll show you. Here, I think the car, the agent, when the agent is trained, you can see basically where it is on the map, on the road. So I think because all of the vehicles are on this side, I think the agent just figured out that it was maybe safer to be here at a given point, and sometimes to be here when there is another vehicle just in front of it. I just think it is like this, but I didn't do anything for the car to be on the right. And I think this is not something that I want, because the goal at the end is to give just a little reward and to reach a very good behavior at the end without saying a lot of rules and things, you know. Because you want to make it generic to apply it to many systems, so you just want to stick to a minimum reward.
So you're not applying rules in this?
No, not at all.
Like that.
Yeah.
But you can do it if you wanted to train the model.
Yeah, I could do it, but it's still something. I would introduce a bias, a human bias, into the algorithm if I done that, and it is not what I want to do. Yeah.
How is the training data generated? Like, did you play with the game for several hours and?
No, this is just. I will explain. Just after that, I will explain how the algorithm is working. But basically, the agent is just trying to explore the environment by itself. So there is no data set at all.
Oh, so it's explored by itself. And
Yeah. Yes.
Yeah, so the LiDAR, so the different states that each of the LiDAR points can take, is it grass, road, and car? Is it
There
just
is,
those
for
three?
the moment, there is just 3 states.
Yeah.
So grass,
Yeah.
road, and other vehicles. Yeah. So yeah, so now I'm going to explain you how this algorithm is working. So I will just try to give you a big overview, intuition of how does it work.
How many LiDAR points are there in that example as well?
Mhm.
How many actual points can it see?
The amount you want, basically you can just customize it to say I want 5 points or 25 points. You can just customize that. So this algorithm is based on 2 neural networks. So this is a deep deterministic policy gradient algorithm. So this is based on 2 functions. So the first function is the action value function. So the goal of this function is to estimate how good is a particular state on a particular action. So if the car, let's say, if the state is the car here, and the action is 1 here and 0 here, it means that we want to accelerate and we are in this position. So here this is something which is bad, because if we continue to accelerate without turning, we are going to go out of the road. So this is the bad state. So the goal of the action value function is to evaluate this state as a bad state. So let's say evaluate this state as -1 to say, okay, if the action value function is good enough to evaluate a particular state, it will return something like this, something negative, because this is not good. But for instance, if the action in this state will be, okay, we don't accelerate so much and we just turn left, then it's good, because we can expect to continue on the road. So here this is a good action. So a good action with this state. So we can expect something to be 5, for instance, here. So here is the goal of the action value function. So the action value function is just a neural network. So taking as input the state of the environment, so the vector with all the points, and a vector of 2 values for the actions. So there is a first neural network here, the first layer here for the state, another layer here for the action. Then we concat everything together, and then we add another layer, and then we just output just one value for the value of the state. Are you familiar with neural network on layers? Yeah. Okay. So here this is just basically all it takes with TensorFlow.js to create this neural network. So first layer here, we just use the layer API to make it very simple. And then we just say the number of units we want, the activation, I want a linear activation. Then we can add a second layer, add buys, add an activation with redo, and at the end just say I want just one unit to predict, and I want a linear value to predict the value of the state on the action. Just that. Okay, so now with the action value function, we want a policy. So a policy is, the goal of the policy is to say how to behave into the environment, which action to take for a particular state. So let's say we are in this state, the policy network will say, for instance, going just, if the policy is bad, the policy could say, okay, just going forward. It will be a bad action, but the goal of the policy is just to predict the two actions to take. So this is here two continuous values. So this is a neural network too. So this one is much more simpler. There is just a first layer for the state, a second layer, and then an output layer of two values for the actions. And once again, this is very straightforward with TensorFlow.js. You can just use the API and create your layers like this. Do you have any question on that? Yeah. So now for the exploration. So as I said, there is no data set. There is the much more easy way to explore the environment is to take the output of the policy, so let's say these actions, and to add some noise on that. So you can, for instance, take a random a Gaussian with a mean and standard deviation, and add this to the actions, and you can just behave differently, not following your policy, but following something which is slightly different to explore your environment. So usually this is a way to do it, but in my environment, in this environment, this is pretty bad because let's say, because we want to accelerate or decelerate. So let's say I am at 0 mean, I add each time a noise with a given mean and a given standard deviation. So I will go sometime above 0 and sometime below 0. So basically what the car will do is the car will just never move because the car will try to accelerate and decelerate at the same time, so the car will just not move, and this is something we want to avoid. So this exploration is good for a lot of problems, but for my problems I use something else, which is a paper which is introduced by OpenAI. This is the parameter space nodes for exploration. So the goal of this method will take another point of view. Instead of adding the noise to the action at the end, you will add the noise directly to the parameters of each of your layers. So I will go here with TensorFlow.js. I will select all my trainable weights, so all my weights into my layers, go through each of the weights and add the noise to the weights. And by doing so, I can create a new behavior for the cars. I can explore my environment by doing like this. This is just much more efficient to explore the environment than just adding a noise at the end. And once again, it's very straightforward to do it with TensorFlow.js. So just to have a big overview of everything, we have the policy. So this is not exactly the same policy. We just follow a perturbated policy with all the noise into the network to explore the environment. We just gather everything, like the state, the action, and the reward, and the other state that the agent can see into a replay buffer. So this is like we create a big, like a little data set, but just by exploring the environment. And from this data set, we just train at the end the action value function to predict the value of one particular state. and then we change the policy to maximize the action to maximize the value of this network. And by doing so, we can just change the action to just get more reward the next time. And then we just go back to here and we explore again, and we're just doing this cycle like this, and at the end the car can be trained. Yeah, so the GitHub is here if you want to check out. You can follow me also on Twitter. Yeah, thank you.